Arborist model finds parents for unseen textual nodes using triplet-loss, StarSpace embeddings, and the shortest path distance. Right, so, there's this interesting problem. Think about having a tree where you want to categorize shopping items, right? And you get a new node, which is called bird supplies, and you are supposed to put it somewhere into the hierarchy. How would you solve this problem, right? Correct answer would be put it under the pet supplies, select pet supplies parent. So, but how would you do this automatically? How would you learn an algorithm which would be able to find a parent for new nodes? So this is what I came across recently, this kind of interesting problem, interesting tasks, and I will tell you more about it. So why do we have taxonomies, right? So we would like to have this hierarchy of concepts for a variety of reasons, which I will go across. For usually there is some kind of use case. So the parents are usually related to, but more general than the children. There could be multiple relationship types at the same time in the taxonomy, and but usually it's some kind of tree, right? So I created this quick taxonomy viewer of the Google Shopping taxonomy, so you can browse through it. So that's one example. Another example would be this Mozilla Web Tools, which is some kind of categorization of websites, right? I've never used it, but I will think about maybe exploring a little bit more. Okay, Penitrus taxonomy. So Penitrus is this website which is something between Facebook and Instagram. It's about sharing images, and you can like the images, and advertisers can advertise in between the images, right? And the thing is, the advertisers need some easy way to get to speak to their customers, the potential customers, right? So how would you do that? Well, so they constructed a taxonomy from their images, which is constructed by manually. They create this manually, forming this is part of it's a relationship. Right now they seem to have about 11,000 nodes, 7 levels deep, right? Expert created. They have these StarSpace embeddings that they learned. So they for the text in the pins they learned StarSpace embedding. I have a post here, so if you want to get summary what the StarSpace embedding is, you can check it out on the website, whatsofcourse.com. By the way, you can subscribe on the YouTube. I will probably go to the other platforms as well, and of course you can subscribe by mail. It's the best way. As well, there is this I created this tool. So if you would like to, if you are missing these serendipitous interactions in your company, if you'd like to, you are working remotely, but you would like to keep meeting the people, you would like to get introduced, but with some people you would like to stay in contact, you can use this tool. And there's this public room called machine learning, and there are a couple of people there. So if you'd like to meet more people, join there. All right, let's continue. So we are at this Pinterest, right? They have this hierarchy where they categorize the images, and at the same time, this taxonomy needs to make sense to the advertisers. They have lots of curators, but it's getting too much work. How do we categorize incoming nodes that come in every day? How do you do this, right? And at the same time, these taxonomies have other use cases. For example, you can use this. Every product could be part of some taxonomy. It can be categorized somewhere, and then you can use it perhaps for a recommendation, or or you can look for some kind of special factors, right? Because every product maybe has a different type of, every category has a different type of, for example, casualness, representation of casualness for shorts may be very different for how the casual flip-flops look like, right? So you can use this even for some kind of similarity things, right? Okay, so but back to the taxonomy. So the problem is that we have a new node and we want to retrieve a parent, right? We have a given taxonomy, we have a new node we want to add, and we want to rank parents, and ideally the right one would be on the top, and as well the ones under them at least wouldn't be too far in the shortest path distance, right, within the taxonomy. So for example, we have a new word Luxor, and we rank potential parents, and the right one is Africa travel. Right? And the other ones apparently they don't seem to be falling very far, and that's what we want. How do we model this, right? How do you do this? Well, actually, how this model works is that for each node, of course, you have this embedding, as I mentioned. They use some kind of textual embeddings that are trained like a StarSpace. I have a StarSpace post you can read on more, and then they have a hyperparameter natural number k. So they have k relatedness matrices, which are then used for the similarity, right? You multiply as a distance metric, you multiply the vectors across the matrix. But there would be a problem. It cannot be that easy. So it's more complicated. We have k of these matrices. These matrices are linearly combined, and we have weights which are specific to each node and to each parent. So we learn those weights and linearly combine matrices using those weights. And once we do this, what happens, right? What's going to happen? So we will allow for the different types of relationships. We will allow for a variation across the taxonomy. So it will become more flexible model. It will have more parameters, and okay, it works for them. So how do they train? They train using triplet-loss, right? So they always want to have a child close to parent, closer than to any non-parent, plus some margin. But how do you select this margin? And how do you make sure that it's not close to all others, right? So to make this scalable, as usual, you want to sample, and you want to select the margin, and they have this trick for selecting margin. They, instead of just setting margin to a constant, they actually select the margin as a normalized shortest path distance. So they have some sort of principled way to first selecting the margin to make sure that the child is close to parent, and if there anything closer, then at least it should be also close in the shortest path across the taxonomy. Why? Because the curator, it's not so hard for the curator to fix these kind of mistakes. Yeah. Okay, and we cannot sum over all. So instead we sample, and how do we sample? We sample the nodes which have high probability of being similar, and we do that by just having a dot product. So if you throw away the matrices for a moment, just do the dot products and sample from that. How do they evaluate it? Well, there's a WordNet dataset which contains hypernames and hyponyms and other kind of relationships between words. So they used that. And there's other dataset. I'm not sure if I'm familiar with that one. And of course they use their own Penitrus dataset. There's this interesting metric, mean reciprocal rank, which is the 1 over rank of the correct parent in the ranked list. And of course, another metric is this shortest path distance in the taxonomy to the correct parent. All right, so how their model does. So compared to the previous model, I think they added only the additional principled way for the margin, which encourages making mistakes not far away in terms of distance in the taxonomy. So they are able to find the parents better than the previous model. On the data set, especially on their data set they want to optimize for, right? And they do better in terms of this mean distance for categorized test samples, right? Okay, so thank you very much. Hope you liked it. If you have questions, let me know, and